Thank you, Rachel. Hello, everyone, and greetings to you wherever you happen to be in the world. I really appreciate you being here today to find out more about a concept-based inquiry approach to mathematics. And we're going to jump right in. Okay, firstly, a little bit of information about me. I was one of the curriculum writers for the IB PYP, Primary Years Program, particularly in the area of mathematics. I was also co-founder, as I think Rachel just mentioned, of the Concept-Based Inquiry Mathematics Project. At one time or another, I've taught mathematics from kindergarten to grade 10. I've been involved in curriculum leadership pretty much all the way through, starting off as a mathematics coordinator and ending up as a director of teaching and learning from K to 12. I live in Adelaide, Australia. I'm married to Jo Fay, who some of you may know from other Professional Learning International courses and workshops. We have 2 grown-up sons, and since last year, we have a beautiful baby granddaughter. Okay, a little bit about the Concept-Based Inquiry Mathematics Project. What is it? Well, as it sort of says on the label, it's really the intersection of the concept-based curriculum and inquiry model, concept-based curriculum and instruction model, inquiry, and mathematics. And I promise you I will add more meat to those very bare bones as we go through. Just a reminder about the copyright issues. Please don't take screenshots or recordings, and any notes that you make are for your personal use only. Thank you very much. We have 4 guiding questions for today's presentation. What can we learn from brain research to inform the way we approach mathematics? What is number sense, and how can we develop it in our students? What do we know about the range of mathematical achievement we have within a classroom? And how does concept-based inquiry support a mathematical mindset? So the first question, what can we learn from brain research to inform the way we approach mathematics? The most significant research from this point of view for today is the phenomenon of compression. And I think that needs a bit of explanation. You all know that when we learn something new, it takes up a lot of our mental space, what we call the working memory, as we think about how does this work, as we make connections between the various components, as we ask questions as we're going along. We all know that process. Just remember back to when you started to learn to drive a car. That's what I'm talking about. But because the brain can only focus on a few ideas at a time, the ideas that we already know well have to be compressed so that they take up just a small space of the brain. This is what compression is. The mathematician William Thurston explains it like this: mathematics is amazingly compressible. You may struggle a long time, step by step, to work through the same process or idea from several different approaches. But once you really understand it and have the mental perspective to see it as a whole, there is a tremendous mental compression. You can file it away, recall it quickly and completely when you need it, and use it as just one step in some other mental process. The insight that goes with this compression is one of the real joys of mathematics. There's a lot to unpack in that one quote, so I'm going to take a little bit of time on this slide. Firstly, learning the mathematics in the first place involves hard work and potentially struggle. Secondly, you saw several approaches. Mathematics is best approached from different perspectives so that we can see the pattern across them. Seeing it as a whole is also very important. And if that reminds you of the mind maps that we use with students when we want them to understand the scope of one of our topics or one of our units of inquiry, then that really is literally what's happening in our brain. We're forming synapses as we connect ideas, as we get that aha moment. And we're building these networks of ideas that belong together and connect together, that are often called schemas. Then you saw in that quote how efficient this compression is. It takes up a little space in our memory, but when we need it, it's all there. It jumps right in, and the full complexity of the understanding is there. And finally, there might be a few of you listening for whom the words mathematics and joy have never been in the same sentence before. I understand that. When Joe Bowler wrote, who's the professor of mathematics education at Stanford University, that I'm sure many of you know and probably adore, in her summary of this research, she says, the brain can only compress concepts. It cannot compress rules and methods. Therefore, students who do not engage in conceptual thinking and instead approach mathematics as a list of rules to be remembered are not engaging in the critical process of compression. So the brain is unable to organize and file ideas away. Instead, it struggles to hold on to lists of methods and rules. As Rachel implied earlier on, this is quite remarkable. We have evolved, this behavior of our brain has evolved to store away complex conceptual connections and networks in our brain in a very small space, so the working memory is not affected. And the fact that this has had survival value for us as a species just fills me with wonder. But at the same time, it's an everyday occurrence. If you think of when you're doing work with figures or numbers or looking at your monthly bank statement, every now and then you are going to need addition. And the minute you need addition, it's right there. You don't have to go and say, oh, how did that work again? It's right there, ready for you to use as part of another process. So while it's quite remarkable, when that work has been done, it's actually part of the toolkit that we use when we use mathematics to deal with issues and concerns and challenges in the world. So at the end of her summary, Joe Bowler says, this is why it is so important to help students approach mathematics conceptually at all times. Now, there's a paradox here. And to help cast some light on that, we're going to do a quick survey. There will be 4 questions, and I'll ask you to write your answers in the chat. Here's the first question. Were you taught mathematics conceptually? Pop your answers into that chat box. Okay, they're all no, yeah. 1 yes, a couple of yeses, primarily no, and 1 in uni, yes. For most people that would be way too late. Okay, not at all, yes, no, to a degree. Not at school, but my father did unintentionally. And another one, not in school, but yes, by my parents. Okay, wise parents. Thank you for that. Second question. If not, how were you taught mathematics? Rote learning, textbooks, rules, memorization, procedures to follow, methods, cramming the rules, procedures, memorization, answering questions from textbooks, formulas, theorems, learn the roles first, worksheets, textbook formula, rote learning, procedural repetition of calculations. Thank you. Third question. Did it work? That approach that you've just listed? No. Yes, but it was hard. For a time, then I forgot. Not developing a love of mathematics. At times, yes, somewhat, up to primary. To this day, maths terrifies me. Some of it, but forgot after a time, up to a certain level, to some extent, and so on. I remember the basics, but not much from high school. Yes, but I feel I did the drilling, but understood the concept later on. I like math better now that I know how to teach it more conceptually. It's a fairly common experience for people when they get to that stage. Or yes, I learned it just to get an exam done. Thank you very much. And the final question. Sorry. There we go. Were there any side effects to that process? It made me hate the subject, lots of tears. Yes, damage to my confidence, self-esteem. I hated maths. I didn't engage with maths anymore. I decided to become a teacher to change it all. Maths is easier now that I'm doing it conceptually. Hated some parts. Geometry was my Achilles heel. I had less agency. I still do not like it. Okay, so this is the paradox. On the one hand, we've got Joe Bowler saying mathematics must be taught conceptually at all times, and yet we have this vast tradition that you've provided just the latest evidence of. This is not unusual, what you've said. This tradition of people feeling that it was about learning rules and procedures. Now, it's very easy with hindsight to look back at that and be critical. But we do need to think back to the time before computers. And I'm old enough to remember that time in life. And before computers, all the numbers work, all the number crunching in societies had to be done by people, by armies of bookkeepers. And they did all the numbers crunching. My mother was a bookkeeper by profession. And I remember going into her office occasionally after work and looking at these beautiful, big, leather-bound ledgers with rows and rows of numbers written down the right-hand side, all by hand and all in pen. Now, nowadays, we don't hear the term bookkeeper anymore. It's basically disappeared because computers have replaced it. But at the time, the school systems, especially the public school systems, felt that it was their obligation to prepare the workforce for this hugely important work. And yet to do that training of teachers in this arithmetic, basically, they didn't exactly have the ideal circumstances. They had classes up to 40, sometimes 50. I remember in my own primary school, I was in a class of over 36 students. When I started teaching, even in the mid-70s, I still had a few classes that had almost 40 students in. So we had to almost do the impossible. And what was decided as a pragmatic result was that we would come up with one standard method that everybody had to learn, even though we now know that brains don't work that way. And there was always one right answer because this was about people's dollars and cents. And the standard algorithms that were developed were largely mechanical. You didn't really need to know place value. You just had to carry the one and so on. And so those methods and procedures became the norm for classrooms around the world. But as we know from the research that I mentioned, those methods and procedures and those rote pieces, they don't compress. And so they were hard to learn, which led to the drill that was mentioned. And what goes with the drill but the drill and the kill? What does it kill? It kills a lifelong love of learning mathematics. And we have the benefits of neuroscience to help us. And those days are long gone. But look how many of you still report, and some of you I know are a lot younger than me, the legacy of that kind of teaching still lives on. How do we deal with that? Well, if we need to learn maths conceptually, we want our students to learn mathematics conceptually, what better way to teach mathematics conceptually than through a concept-based inquiry project? Now, what does that have to offer? what does concept-based as an approach have to offer? For those of you who may be a little less familiar, I'm just going to do a brief overview of what concept-based offers. And again, just talking about the nature of mathematics and why we need a conceptual approach. But here's a quote from Erickson, Lanning, and French, who are the stalwarts of concept-based curriculum and instruction. Mathematics as a subject is inherently conceptual. It's a language of concepts, subconcepts, and their relationships. And while we start out with real concrete objects in the early years of schooling, objects and materials, cubes and blocks, maths becomes steadily more abstract. And it's actually abstract to think about this process too. So I've come up with a visual model that I hope becomes a kind of metaphor for the process of increasingly abstract learning. Imagine that each concept and each understanding is a brick in a structure like this. And the reason this metaphor, I think, works is because we build new concepts on the foundation of previous concepts, and so that these concepts can become increasingly more abstract. I definitely need to provide an example at this point. So let's think about the understanding of addition. We need to understand addition well before we introduce multiplication, because multiplication is best understood initially as repeated addition. So multiplication is built in our brains on the solid foundation of addition. And then it takes another couple of years to become really proficient with multiplication before we introduce exponents, which again is the repeated multiplication of 10 to the power 4. Sehen hoch 4 in German, for example. And so imagine for one moment if we walked into school and started teaching students exponents. Imagine how we would have to then try and backfill all the understandings, all the conceptual work that went beforehand. So I hope that's a helpful example to understand the visual model. And this is happening right across mathematics. We're building ever more refined, ever more abstract understandings on the basis of the previous building blocks in the structure. This is known as the hierarchy of abstractions. And mathematics is basically the only subject where this happens right across everything. But because of that, a concept approach makes such good sense. So just a bit of a review of curriculum in general. Most of the curricula that you will find and that you're working from are called two-dimensional. They stipulate the skills and the knowledge that students need to learn and that needs to be assessed, but they rarely specify the understanding that goes with that. Whereas in a three-dimensional model, such as concept-based curriculum and instruction, developed by Lynn Erickson and Lois Lanning, and it's been around for quite some time with a lot of proponents, understanding is added as the third dimension. And it's added explicitly, and I'll explain that word explicit in a minute because it's a bit loaded, explicit. So this doesn't mean that understanding is not important in the 2D curricula, but it's not specified. And it's, I suspect, because it's actually hard to do, as we now know, having done it. So what does concept-based inquiry offer in the classroom as practical ways to help students understand concepts? One of the targeted strategies you can see here is used to introduce new concepts usually earlier on in a unit. It's called a concept formation strategy. The one you can see here is an example of a Freya model. Freya model has 4 parts. One part is for the definition, one part is for facts or characteristics, one part is for examples, and the other part that is covered up here is for non-examples. And groups of students working collaboratively will fill this in from their learning and their experiences and build an understanding of what addition is. In this case, I think it's a whole class one that was used for review before moving on to something else. But the principle is the same. So there are specific strategies that are used throughout concept-based inquiry mathematics that support the learning, and I say explicit, but the specific, the intentional learning of new concepts. But it's not just concepts that concept-based inquiry provides. We also provide the conceptual understandings that drive the mathematical learning. These are called generalizations. What is a generalization? Here we have a quote: generalizations are by definition two or more concepts stated in a sentence of relationship that transferred through time and across cultures and situations. We need to look at some examples. So here in our scope and sequence, you will find a number and number sense at phase 3. In a place value system, the value of a digit depends on its place in the number. Does that make sense to you as a summary of how number systems work? Or partitioning, phase 5. The greater the number of equal parts, the smaller each part becomes. Measurement. When measuring, grade 1, people arrange the units so there are no gaps or overlaps. Number operations, phase 8. What people do with the remainder depends on the context of the problem. So as you can see, for the teacher, the conceptual learning is made fully explicit so they can know where the learning is going. Primary teachers often say that they don't feel confident about where it's going next and where to take the students next. This is provided for the students. But we don't give these generalizations explicitly to the students. We don't put them up on the wall and unpack them or unwrap them or analyze them. The students instead are guided through carefully crafted sequence of learning engagements to the point where they are able to express these generalizations in their own words. That's why they're called generalizations, because they then have generalized, they've made a general rule from their own learning experiences. So that's why we as teachers, when we write these generalizations, we write them in age-appropriate language that students can then understand. Now, as some of you indicated in the chat earlier on, some of the students work these out for themselves. They may not articulate them, they may not verbalize them, but they work out the understanding for themselves, as some of you indicated. In my experience, it's been somewhere between 15 and maybe 25% of students just get the mathematics and and then apply that almost effortlessly. But 75 to 85% is a pretty bad, miss rate. So we need to do something. We need to do something better. I'd just like to unpack the definition that you saw earlier on. Generalizations are two or more concepts stated in a sentence of relationship. If you look at this first generalization, place value is a concept. Number system is a concept. Value is a concept. Digit is a concept. Place is a concept. Number is a concept. So we already have 6 different concepts, and I know some of them are related in one generalization. And then the rest of the sentence explains the relationship, the statement of relationship between those concepts. The value of that digit, of each digit, depends on its place in a number. Not only that, but this understanding is universal. If you think about it, it applies to all numbers and digits. And even though in grade 2, students won't have learned about numbers up to millions beyond or decimals, some of them won't. This unit, this understanding will still apply in grade 4 and so on when decimals are introduced. At which stage we can ask students to test their old generalization. Is that still valid, this generalization, for these new numbers that we're learning about? So this becomes an opportunity for us to discuss and think about abstract ideas with our students in a language and based on experiences that they've had. I just want to give you a couple of examples of how students write their generalizations. They don't come out the way we've worded them, but we can use that as a kind of benchmark. So in this is about in grade 4, this is about remainders in division. And students write things like, the amounts of things are not always perfect. You might get some left over or a remainder when you're using division or dividing things. Division isn't always perfect. You sometimes get a remainder. Also, you can make a remainder into a fraction. So already the teacher brain is saying, aha, this student is making some connections from what's left over in division to the fact that that can be expressed as a fraction, and so on. Obviously, with our youngest students, writing generalizations, creating generalizations is actually an oral exercise, usually in small groups, often with materials with them on the floor. I was talking to a teacher just this week. She was talking about the very first unit, kindergarten, and it was about counting. And 2 of the students had written a generalization or said a generalization that the teacher scribed. There are lots and lots of wrong ways to count. What a lovely 5-year-old's perspective on counting. Another one in the class wrote, some kids try and can't get counting right. So they're generalizing from their experience in this unit. But of course, this is a great opportunity for a teacher to follow up with the student and to probe their understanding, so that the teacher is really confident that they've understood. It's almost like a mini writing conference because the student has produced some text. It becomes like conferences we use in our writing lessons. The other thing that connects back to the research, and this is again really significant, I think, it's language that enables those important phenomena, those important concepts, to be named as thinkable concepts that can then be refined and connected together into coherent frameworks. I realize that's highly abstract, but it's talking about, it's language that helps us to develop the concepts that can be then compressed and used whenever we need them. So just to summarize, there's a danger when we're just working with skills and curriculum as the bits that we're accountable for as teachers and that we want our students to acquire. Because there are so many skills and so much knowledge, if that's not bound together in the structure of a conceptual structure, there's a danger that the curriculum can become coverage-centered, and that often looks like mile wide and inch deep. And it's the deeper thinking that we really need for our students nowadays. Whereas in a 3-dimensional curriculum, it's meaning-centered. It's the understanding that's important, because that's how our brains know how to compress, and that's how we become fluent at using these schemas, these understandings as tools in the work we do, both within schools and within our career and at home with our mathematics applications. Okay, moving on now to our second guiding question. What is number sense and how can we develop it in our students? It was really only in the late 80s that the term number sense started to be heard, as researchers and commentators were all pretty much agreeing that improved number sense is the desired outcome of mathematics education. So what is number sense? This is quite a useful explanation. The term number sense refers to several important but elusive capabilities, including flexible mental computation, numerical estimation, and quantitative judgment. And why is that important? How does it make a difference? There was some extensive research carried out in the UK that gives us some clues. I just briefly outlined the experimental conditions. In the research project, the students were aged between 7 to 13, and whom the teachers had nominated as low, middle, or high achievers. They were given a range of number problems, and they were asked how they worked them out. And there was important distinction and difference that the researchers noticed between the high and the low achieving students. They found that the high achieving students solved the questions by using what is known as number sets. They interacted with the numbers flexibly and conceptually. The low achieving students used no number sets and seemed to believe that their role was to recall and use a standard method, even when this was difficult to do. Let's look at a couple of examples. They gave students the problem 21 minus 6. And it's helpful to see what many of the low achievers did. They counted back from 6 because that's what subtraction means. Whereas many of the high achievers renamed the problem as 20 minus 5. So for the ones counting back 6, that's actually harder and you're more likely to make a mistake, especially counting back that many. Whereas the ones who renamed the problem to 20 minus 5 had an answer instantly through their awareness of numbers and the relationships and their relationships with a minimal chance of error. Here's a second example. The problem here was 19 plus 22 equals what plus 20? And again, it's really instructive to see the difference. The low achievers tended to do 2 additions procedurally, i.e. as in columns, not mentally, whereas the high achievers saw a connection between the 19 on one side of the equation and the 20 on the other, and then simply adjusted the other number to get an answer. And again, as a mental process, that was done very quickly. Now, it's not that the low achievers didn't get the right answer some of the time, but they used longer methods that took longer with greater likelihood of error because they were clinging to procedures that they felt they had to use. And of course, if students have only experienced, thinking of the high achievers method, if students have only experienced the equal sign as, here comes the answer box, they will be less likely to have developed a rich understanding of the concept of equality, which becomes so important as students move into algebra. So it wasn't that they didn't know less, they just didn't use numbers flexibly. Probably because they'd been set on the wrong pathway from an early age of trying to memorize methods and number facts instead of interacting with numbers flexibly. And of course, when students are memorizing procedures, they're unlikely to compress them and get that super efficiency that comes. Interestingly, this problem is not new. Already in 1961, the mathematician and educator W. Sawyer wrote, "The depressing thing about arithmetic badly taught is that it destroys a child's intellect and to some extent his integrity. Before they are taught arithmetic, children will not give their assent to utter nonsense. Afterwards, they will." And of course, if you're following a procedure without looking at the sense that the numbers you're manipulating make, if you do make an error, you're unlikely to notice. So you may actually hand up or produce an answer that is nonsense from the point of view of meaning. Of course, we've come a long way since then. I don't wish to imply we haven't. But the research on fixed mindset that's come out in the last 10, 15 years really shows us that we are still producing students who leave school believing that mathematics is about learning procedures and methods and applying them almost religiously, dare I say. Incidentally, this problem is a pretty good indicator, as some of you may know, as to whether a student from grade 3 up is using number sense. If they start crossing out those numbers and renaming, and that becomes a 10, and then cross out the 10 and a 9, and that, then you know they're operating procedurally. Students that are working conceptually will see the placed value sitting there begging to be used as they count backwards and flip from a 4-digit number to a 3-digit number. Hopefully these examples show you how desirable number sense of our students having number sense is. But how can we develop number sense in our students? That was what the question was. Our first instinct of teachers, as teachers, is to explain. Teaching as explaining is part of our cultural DNA. Tell Humphreys and Parker, tell us. And it's a very good quote, isn't it? We default to explaining very easily. And I like the way of expressing it, that if teaching were telling, we'd all be geniuses, because we've been told many times. The problem is, the minute we start to explain, we take little bits of their ideas and their autonomy as thinkers away. We, in essence, do the thinking for them, robbing them of the emerging and often fragile authority they have over their own reasoning. That is a beautiful quote. So we really need to break the habit of doing the thinking for our students. Okay, the next instinct of a teacher is to treat number sense as a set of skills, to try to design good, clever learning engagements to help students acquire those skills. Now, it's very easy, though, for skills practice to revert to becoming procedural. And this quote from Constance Camille is a lovely, thoughtful provocation for us. She wrote, "We must beware of teaching students to write correct answers. Not to think about the meaning of what they're doing, but to write correct answers." That's a great topic for a reflection in a staff meeting. Are we teaching our students to write correct answers? Or are we teaching them to understand the number system and how answers are reached and why the methods and systems work and how different ways can be used to get the same answer? So what is it that develops number sense in our students? Dr. H. Howden was one of the early advocates of number sense. And in 1989, he wrote, "Number sense can be described as good intuition about numbers and their relationships. It develops gradually as a result of exploring numbers, visualizing them in a variety of contexts, and relating them in ways that are not limited by traditional algorithms." So the intuition, but it comes from doing mathematical things. But he's also very explicit about what that does and doesn't look like. Since textbooks are limited to paper and pencil orientation, they can only suggest ideas to be investigated. They cannot replace the doing of mathematics that is essential for the development of number sense. No substitute exists for a skillful teacher and an environment that fosters curiosity and exploration at all levels. And I believe you can substitute worksheet for textbook in that quote, and it's still valid. So what does this doing mathematics really look like? Because it sounds abstract. Well, I went through the literature on number sense and collated a number of indicators of what that environment that fosters curiosity and exploration can look like. So we've got teachers and students engaging in conversations, developing and negotiating meanings of terms and making sense of numbers and quantities in situations, collaborating, working with concrete materials, composing and recomposing different arrangements and representations of numbers, investigating the realistic uses of numbers in their everyday work, and so on. And look at those verbs: engage, develop, negotiate, compose, investigate, explore, create. Those are powerful words that describe the doing of mathematics, the active doing of mathematics. We worked hard to routinely include all of these in the learning engagements that we created in concept-based inquiry in mathematics to guide our students towards their understanding. And they also align well with the inductive approach that concept-based inquiry mathematics takes to learning in general, valuing students as thinkers who are capable of learning the abstract, complex ideas of mathematics. And so we use all of those engagements that we've developed, following the concept-based inquiry model developed by Marshall and French not that long ago, using this inductive approach. And here's just a few of the conceptual understandings that we've written about developing number sense. So in number operations, phase 3, people can break numbers apart to help solve addition and subtraction problems. Phase 4, learning a range of strategies helps people work flexibly, that word again, and efficiently with numbers. At phase 5, people can use a series of steps to create a pathway to a solution, thinking of those multi-step problems that come in. And in partitioning at phase 6, people use models and reference to understand and compare the magnitude of fractions. There's good research that shows when students understand the size of a fraction, the magnitude, not just how to manipulate it in equations, they are well prepared for the more complex levels of multiplication and division of fractions that will come in middle school. For those of you that are more familiar with concept-based, these are obviously process generalizations, focusing on the strategies rather than the conceptual knowledge. And these generalizations that I've just shared sit well, I think, within the elusive, important but elusive capabilities that are considered to be at the heart of number sense. And so by doing mathematics in these different ways, within a strong conceptual framework, students in concept-based inquiry mathematics schools are developing number sense at the same time as they work towards the other important mathematical learning outcomes. We move on to the third guiding question, where I'll look at the research that supports a concept-based inquiry approach to mathematics. What do we know about the range of mathematical achievement we have within a classroom? Obviously, children begin school at very different points in their development, socially, cognitively, emotionally, psychomotor, and so on. So rather than being at a similar stage in their learning, students in any given year are spread over a wide range of achievement levels. We decided to look at the research around that. So the research from the US, from the UK and Australia confirms that in any given year of primary school, the most advanced learners can be at least 5 or 6 years ahead of the least advanced students. And anyone who teaches in a primary classroom will have noticed that this is particularly true in the number strands, more so than, say, some of the other strands of geometry or shape and space. To put this another way, Dylan William, attainment is only loosely related to age. And yet students move forward through school in their age cohorts for good reasons. The research also continues that the observation that students in the tail of the distribution, so at the lower achievement levels, fall further behind each year of school. And this may well be the result of exposure to year-level mathematics curricula that are increasingly distant from and irrelevant to their actual learning needs. So if you're in grade 2, we're going to give you the grade 2 curriculum because that's the way it goes. I'm parodying, of course. It's not all rosy at the other end of the achievement scale either. More advanced students in one research project, in one research study, more advanced students in a class often remain unchallenged and make limited progress. When I read that, I think back to some of the classes I taught where the students who scored well on the tasks I gave them, they probably already knew the content before starting the tasks. And while this doesn't actually often present a major problem for the teacher, the effects are nonetheless clear. Boredom, disengagement, underperformance is probably more significant even. And from a mindset point of view, they receive praise and kudos for actually minimum effort. And that's also damaging. So how do we manage this conundrum? Going back a bit now, the most important single factor influencing learning is what the learner already knows. Ascertain this and teach him, her, accordingly. Ausable in 1968. This is clearly not knowledge, and I know, and I'm not denying that we know that differentiation is not optional. We know that as a profession. In mathematics, in the math classroom, the most common form of differentiation, though, is by skill level. So we're all working on multiplication, for example, but the level of difficulty varies with the most challenged students maybe going back to arrays and area models, and the most advanced students creating their own problems, for example. In their book, How People Learn, Brain, Mind, Experience, and School, Bransford, Brown, and Cocking say cognitive changes do not result from mere accretion of information, but are due to processes involved in conceptual reorganization. So it's not just more skill practice that's leading to cognitive changes. In most cases, it's the conceptual reorganization that's important. And skill instruction also doesn't necessarily imply addressing the conceptual understanding. As I said before, it may point students to procedural practice to get these damn things right, rather than conceptual learning. So the researchers in this case concluded there's a good deal of evidence that learning is enhanced when teachers pay attention to the knowledge and beliefs that students bring to the learning task and use this knowledge as a starting point for new instruction. Now, each scope and sequence that we have written for concept-based inquiry mathematics was written as a progression of conceptual understandings, leading students steadily up the hierarchy of abstractions. And while the skills may progress steadily, and if you look across here, you can see, okay, familiar number relationships up to 5, familiar relationships with 10, familiar relationships up to 20, familiar relationships up to 100, etc. While that may work smoothly, if we look at the understandings, they are very different because conceptual understandings builds. It doesn't necessarily just repeat. So in a class, let's say a grade 2 class, you could have students working on the understanding that numbers can be added more efficiently by counting on from a large number. And other students are learning that people can solve multiplication divisions by visualizing patterns in an array. It's going to be very hard to unify those learning needs into one set of lesson plans. And yes, phase 8 is the top end of our current progression. So by looking at this and looking at the research and thinking about our collective experience of trying different models of differentiation, we decided after much deliberation that learning in the number strands, that's number and number sense, number operations and partitioning, but learning in those 3 strands is achieved through developmental phases as the best way to manage the range of achievement levels in a class and work from students' current knowledge. And we believe that when students are learning at an appropriate level to their developmental needs, and when the scope and sequence is constructed as a conceptual progression, then students can progress in their understanding of the increasingly abstract ideas of mathematics. And I do want to stress that placement in one of these phases in our project is just for the duration of that particular unit, or less if new evidence emerges during the learning engagements that the student actually does understand this. So putting students into phases based on their needs places a huge premium on being able to determine and monitor what students already do know. Unfortunately, there are more than one ways to do this. The first I'll explain is a strategy that's colorfully known as the mess about, and it's done at the start of the unit. These are the instructions we give. Give students time to explore the manipulatives that you'll be using throughout the unit. This helps them to tap into their prior knowledge. Adopt an inquiry approach. What do you notice about these materials? Have the students make observations and wonderings. And then you as a teacher can observe and gather anecdotal information on a checklist as they're doing this. And here are some of the suggestions for the stations that you might have in a classroom while the students are doing these things. They include, for example, literacy. Have some number-related books, and we provide lists of those for students. Some games that can be played, some maths journals that can be used for some problem solving. What the feedback we're getting from schools that are already implementing concept-based inquiry mathematics is that the students love the mess about. They seem to like the freedom to explore, the time to explore, the playful approach. It deals with often with their anxiety, lowers their levels of anxiety if they have that. It's the beginning of self-directed inquiry. The teachers are also reporting that they love the mess about. For once, they're actually not having to teach. Their role is to observe, to make notes, not to go in and not to leap in. And one teacher said in a meeting recently, I got evidence of students already knowing what I was about to teach just from the mess about. We also have developed a series of pre-assessment tasks. We needed to be careful that this wasn't about skill performance because that's easy to assess, but we wanted understanding. So in response to this challenge, we developed pre-assessments that in as time-efficient and age-appropriate a manner as possible, we can find out what the students already know and understand. Obviously, with much younger students, this is done in a much more hands-on way, orally, in some cases in a one-on-one interview. But it allows the teacher to gain that understanding of what the student needs next conceptually. I must have to say, this was fairly new for most of us. There were a few diagnostic tools that we were inspired by, and this one we were actually given permission to use. These were developed by Professor Di Seaman of the Royal Melbourne Institute of Technology for the state of Victoria education system in Australia. And these are some more of those conceptual diagnostic understandings, which I will move on quickly from now. So we're proposing that students in the number strands work in phases to best address their learning and their needs in a conceptual way. The final question, I hope I'm just about squeezing in on time. How does concept-based inquiry support a mathematical mindset? And again, we know that there's been huge, and again, it really is truly fabulous research into not just the mathematics we know, but the beliefs that we adopt about ourselves as learners of mathematics. This won't take long. Joe Bowler, again, approaching mathematics conceptually is the essence of what I describe as a mathematical mindset. So we're increasingly confident in the feedback we're getting from the schools that are currently on the pilot, that the experiences that we're providing, the tools that we're giving teachers through the Concept-Based Inquiry Mathematics Project is helping them, A, to learn the mathematics, but also to develop a mathematical mindset that will set them up for their learning right through school and their life. That's it. Thank you very much for your attention. I hope that's been helpful, and I hope as you go through the remaining parts of the summit that will help connect conceptually to what you're seeing practically in the classrooms. Thank you very much.